Okay, so let's continue with our discussion of waves. So this is video number 3. So just a recap of what we covered. We talked a lot about this formula called the velocity formula for our waves. Here, velocity is equal to your wavelength times your frequency, and frequency is the number of wavelengths that are passing through a point per second. So here in this example, you have 2 wavelengths that are passing through a point, and that's 2 hertz, and each wavelength is 3 meters. So our speed becomes 3 by 2, which is 6 meters per second. And we said this is true for all the waves that you're going to come across. So let's look at this example again here, where now your wavelength is 1 meter. And let's get to know something about frequency. What is the frequency of this? We are told that the frequency is 1 hertz. So we're going to have 1 full wavelength passing through a point per second, and a full wavelength in this case is 1 meter. So 1 times 1. So that means our wave is going to be traveling at a speed of 1 meter per second. So after a second, the wave would have passed, would have moved 1 meter from our reference point. Okay, so if I tell you that the frequency is 4 hertz, so this is hertz, but however here my wavelength is still 1 meter, so 4 hertz per second, it means I can pass 4 full wavelengths per second. So this frequency is a high frequency compared to the previous example. However, my wavelength is still the same. All I need to do is to say 1 meter times 4, and I get 4 meters per second. So after 1 second, this wave would have traveled 4 meters. After 1 second, this wave would have traveled 4 meters. The previous one, after 1 second, its frequency is simply 1 hertz. After 1 second, it would have traveled 1 meter because the wavelength is 1 meter. And after 1 second, this wavelength can only cover 1 full wavelength. That's what the frequency is telling us. It's telling us after 1 second, this wave would have traveled 1 full wavelength, and our full wavelength is 1 meter. This frequency tells us that after 1 second, you would have traveled 4 full wavelengths, and in this case our wavelength is still 1 meter, and therefore in 1 second we would have traveled 4 times our wavelength, which is 1 meter. So that's 4 meters. That is what is implied by our speed there, and you can see that this is what this formula is trying to help you to do and understand. So let's proceed to talk about displacement distance graphs for waves. So I figured out it's important that you understand these 2 graphs. So we're going to be looking at the displacement distance graph, and the other one is the displacement time graph. So let me just have these graphs side by side so that you understand what I'm trying to say. So let's begin here. So the displacement distance graph is going to show you the displacement, remember, of the particle. Remember, we said that when a wave encounters a particle of matter, it oscillates that particle of matter. It doesn't carry it along with it. So what happens is this graph is telling you the amplitude, how far from an equilibrium position the wave is going to carry your particle of matter, but it would compare that now with the distance or the wavelength that the wave would have traveled. So we are talking about the distance traveled by the particle during oscillation, and the distance that is covered by the wave as it oscillates that particle. And so this graph can give us our wavelength. So you can just measure from crest to crest or trough to trough, and you realize your wavelength, your lambda. On the other hand, if you traced the particle, it's displaced. In this case, our amplitude is the same, it's 0.75 meters. So your particle is going to be displaced 0.75 meters from a neutral position here. But this graph now tells you how long that takes for it to have a full wave cycle, that is to go up and down and back to the original position. So up, when this part of the wave passes, it's going to go up, and it's going to go down, and it's going to go back to its original position. We saw that in previous animations, you can check. and it's telling you how long this is going to take. And we said the time it takes for us to have a full oscillation or a full wavelength passing through a point is referred to as the period. So it's this graph can be analyzed to give you your period. So we are saying you must be familiar with those two graphs. And you can find your frequency from this graph. You can say 1 over your t, and in this case it's 0.125 hertz. And from this graph I can find my wavelength, and if I have those two, I can find my velocity, in which case becomes 2 meters times 0.125 hertz, and I have my velocity of 0.25 meters per second. So it's important that you know these two types of graphs: the displacement time graph, which you can use to figure out your period, or your displacement distance graph, which you can use to find amplitude and also wavelength, but most importantly wavelength here. And you saw that both graphs have the same amplitude in this case. So I needed to emphasize on that. Now let's talk about electromagnetic waves. Electromagnetic waves. So this can be defined as periodic vibrations of electric and magnetic field intensity that move through space. Periodic variations of electric and magnetic field intensity that move through space. The oscillating electric and magnetic fields exist at 90-degree angles to each other and are in phase. We'll talk about being in phase and out of phase in different videos, but you should know that they the intensities, the peaks are going to be at the same time. They're going to happen at the same time, and the troughs are going to also occur at the same time for both the electric field and the magnetic field. This is what it simply means. Okay. So examples of electromagnetic waves, you saw this in the previous video: light, microwaves, radio waves, infrared waves, gamma rays, etc. So we'll look at these in detail. So let's move to the next points here. Electric fields and magnetic fields can both exist in an empty space. So this is the only type of wave that can travel through a vacuum or empty space. So the rest of the waves, mechanical waves, they require a medium. Your ocean waves, your sound, they require a medium. However, only these can travel through an empty space. Okay, this is what your light does as it passes from the sun to the earth. Okay, the wavelength of an EM is the length between two crests, just like any other wave, any other transverse wave, or the magnetic field strength. EM waves can have any wavelength and frequency. So here's something that's special about all our electromagnetic waves. They all move or travel at the speed of light, which is lowercase c. 3 times 10 to the power 8 meters per second. They all travel at the same speed. So because the velocity is always c, all of them will obey this equation. C is equal to your wavelength times your frequency. So since our speed or velocity for all these waves is equal, what it means is that if you increase your frequency, then your wavelength is going to decrease. That is to maintain our constant speed. If you increase your frequency, your wavelength has to decrease, and vice versa. If you increase your wavelength, then your frequency has to decrease. And we can see this in our electromagnetic spectrum that we'll look at later. So we should also know that when we have a high frequency, then this means that that wave carries a lot of energy than when we have a lower frequency. So high frequency waves will carry a lot of energy compared to low frequency waves. So here's our electromagnetic spectrum and the types of waves that you can see there. Let me show it again in a different diagram. Okay, so this is the electromagnetic spectrum. You can see that we begin with our radio waves, microwaves, infrared, red, orange, yellow, green, blue, indigo, violet, ultraviolet, x-rays, and gamma rays. And as you go down, what's happening?